Are you a data scientist lost in exploration? Is it the first phase in your data science project, but you feel overwhelmed and lost already, failing to make any progress? What if I told you that the key to an efficient exploratory data analysis are just some structure and an agile mindset? Hi, I'm Joanna, a senior data scientist, and in this video I'll share with you my approach to exploratory data analysis that I've refined over the years. It helps me stay focused, organized, and deliver value every single time. So brace up, because we will deep dive into the heart failure prediction dataset, hands-on, using Python. Understanding the data is the make it or break it of any data science project. It comes first, before any other step, and it sets the foundation for drawing conclusions that make sense. It helps also understand what would be a valuable question to answer with the data. Because of its importance, probably so many of us have at one point in our careers fallen into the trap of the never-ending data understanding. So data exploration must come with a deadline. Keep in mind that data science is an iterative process, so most probably we will end up in this phase sometimes in the future. Don't try to understand everything at once, and most importantly, don't try to understand it by yourself. Because when going beyond university projects, there will be somebody who usually knows more about the data than the data scientists do, so reach out to them for clarifications. Personally, when I perform exploratory data analysis, I also do some data cleaning as I go, just for the sake of relevant reporting. I view exploratory data analysis from two perspectives: the structure perspective and the reasoning perspective. Structure refers to everything that's quantitative about the dataset, like the number of rows, the number of columns, how many duplicated rows I have, or how many missing values my dataset has. The reasoning step involves me learning more about the data, understanding the business, understanding the process that generates the data that I'm going to work with. I look up on Google the terms that I don't understand. I look into the variables consistency. I try to see that the data that I'm going to work with makes sense. Moreover, I'm also going to look into discovering some outliers and then later on decide what to do with them. This is the stage where I also generate visualizations that make sense for my dataset and also for the purpose that I have. Thanks to how I structure the exploratory data analysis process, by the end of it I have a clear idea of what the next steps should be, how to treat the missing values, what to do with the outliers, how to perform feature engineering. I'll know whether there is some data transformation needed for my data set for some variables, or if normalization or standardization is required to get better results. If I don't have a question already that must be answered with that data, I'll also have a short list of potential problems that I could solve with the data. And at the same time, I'll have an idea of what models could be suitable to address those problems. So let's roll up our sleeves and do some exploratory data analysis.
We are going to use the heart failure prediction dataset from Kaggle in order to perform this exploratory data analysis. You can download the dataset yourself from the link in the description. The dataset contains 12 features that can be used to predict mortality by heart failure, because cardiovascular diseases are the number one cause of death globally, resulting in 31% of all deaths worldwide. The interesting fact is that most cardiovascular diseases can be prevented, and there are certain risk factors that can increase the likelihood of developing a cardiovascular disease, such as hypertension, diabetes, lack of physical activity, smoking, and so on. So the first thing that we are going to do is import the packages that we'll be working with. We are importing pandas and also NumPy, the package based on which pandas is built. Next, we are going to import the packages for visualizations, which are Seaborn, Matplotlib, and then we are going to define the plotting style, which is going to be ggplot. The next step is to load the dataset. I downloaded it on my computer, and I'll be using the read CSV command from the pandas package, specifying the path. Then check if it loaded correctly by just printing the first 3 rows of my data frame. The default is 5 rows, so if you don't specify any number here, it will just print the first 5 rows. Our data has loaded correctly. We see that the index is on the first column, and then the age, anemia, and other features are following. Regarding the dataset structure, I'm going to inspect the number of rows and columns, the column names. So the data shape command is just going to print the number of rows on the first position of the tuple and the number of columns on the second position of the tuple. And then the columns command is printing the name of all the columns. For the sake of consistency, I'm just going to lower all the column names by using list comprehension. Indeed, now all the column names are lowercase. The next thing that I want to discover about my data set is whether it has duplicates or not. There is a simple command that generates the number of duplicated rows. If we use data duplicated, we are going to get a boolean with false where the row is not a duplicate and true where it is a duplicate. So just summing up this boolean vector is just going to add up all the true values and compute the number of duplicated rows. This can be useful for a report that we are going to write. So we are going to just print it. And if we also want to see which of these rows are duplicated, what we can do is simply select only those rows that are true in the Boolean array. This is going to result in the 10 rows that are duplicates. So by inspecting these rows, we can see that many of them have none values. There are some causes why this could happen. For example, if a data set was concatenated from multiple sources, it was not properly cleaned. This is something that we'll have to investigate a bit further, and we are going to do it in the missing value analysis step. We are going to perform a missing value analysis that goes a bit beyond just counting the number of missing values. We are going to print first the missing values in the data set with the isNA command, giving us true, false over all the cells in our data frame. True where the value is an NA and false where the value is other than NA. If we sum them all, we are going to see the number of missing values by column. What we want to do is display the number of missing values versus the number of valid values by column. So for that, we are going to create a bar plot. And this is the first visualization that we are going to use in this exploratory data analysis. The first step is to rename the columns. So we created this new column that's called valid, and it consists of the values that are actually valid for each column. And we use least comprehension for calculating it as the difference between the length of the data set, or the number of rows in the data set, and the number of missing values. What we can do now is just plot directly from this data frame. So instead of table, now we have a visualization. We see here at the bottom that we don't have the column names, but actually we have some numbers, some indices. These are the indices of the data frame. So one thing that we need to do additionally is reset the index to be just the column's name. Column names are represented by each of the bars, and with red we have the missing values, and with blue we have valid values. One thing that we can do is just save this as an axis, save the plot as an axis, and then additionally we can use all the axis properties. For example, we can set a title. We can also set the X and Y labels. And then here we have already the column, so let's see how it looks now. So again, if we do is NA and then we sum, we get exactly what we've done before, but if we sum again, then we'll see that our data frame has in total 102 missing values. So this is going to be total nones. It is a number that we are going to report also. Next, what we want to investigate is the number of rows with missing values. As we have seen from our data set, there are some rows only with missing values, and there might be some rows that contain missing values only on some of the columns. In order to calculate the number of rows with missing values, we are just going to change the axis. This is our Boolean, so if we sum it up, we are just going to receive the number of rows that have at least one missing value. Next, we want to see the number of rows which are full NA. And now instead of any, we are going to use all. X is equal to 1 because we are looking at rows, and sum everything up. The next thing I would like to visualize is the percentage of missing values per row, and I am going to divide it by the number of columns. And this is going to give me the percentage of missing values per row, where the number is 1 we would have a row which only contains NAs. I can visualize this with a histogram. Okay, so here is my histogram, which indicates that the majority of the rows don't contain any null value. These rows don't encode any information in it, so the best thing is to remove it. Actually, I'm going to remove all the rows that contain any none value. We can use drop NA to remove all rows that contain any value, and we are going to save this dataset. Prove the fact that we removed all the rows that contain missing values. I'm also going to remove the duplicates. Okay, so the data shape is going to actually indicate that I also removed the duplicated values. Next, what I'm going to do is explore the data types. Data types refer to the type of value within each column, and they can be accessed by just typing the types on the data frame. Except the last column, which is a string column, all the other ones are float. But this is very unlikely. So what we can do is just replace the data types of the columns which are not numerical by defining a dictionary where each key is the name of the column and each value is the data type of that column. By running this, we can see that we've changed the data types on the specified columns. We have another variable, age, an integer value. The reason I'm doing this is that it is not possible to directly change a float 64 into an integer value unless you floor the value. And now we are just going to look at the data types again and see that age has been changed to int64. So now all our data types are correct. I would ask myself, why do we have two columns here, death event and death event S, and what's the difference between these two? In order to check the difference, I am just going to select these two columns from the data frame. Now what I see is actually that the true of death event corresponds to the string dead. So probably death event is the Boolean version of the variable, where death event S is the string version of the variable. I'm also noticing here that there are different versions of the string. The next thing I'm going to do is inspect the string variables. We can subset the data frame. We are going to exclude all the numerical variables, that's float 64 and int 64 respectively. We can use the method describe to get the summary statistics for these columns. So we see that anemia has two values, diabetes has two values, death event S has 4 values. So what I want to do further is see which are these 4 values. This will give me the 4 categories of this column. Now what I see is actually that my strings are not consistent, and I want to correct for these strings. So I'm going to perform a string processing at this step. First, I'm going to lowercase the values of the string, and then I'm going to use strip to drop all the spaces. I see that I still have one problem here with the typo. In order to correct this typo, what I have to do is just replace it. And now I see that actually my variable contains only the two values, which are dead and alive. I'm just going to run this cell again to prove that my preprocessing returned the expected results. Okay, so this step is part of the reasoning perspective that I was previously mentioning, where I'm just asking myself, do these values make sense or not? One additional thing that I would change is defining the sex as female or male instead of 0, 1. Now I'm interested in also checking the summary statistics for the numerical variables, and in order to do this, just going to include the numerical variables. Here I can see the number of values that I have for each variable. I can see some summary statistics, the mean, the standard deviation, the minimum and maximum value, and also some quantiles. My first impression is that there will be some data processing needed. There will be some data standardization that will have to apply in the data processing phase, because the values are quite different in a range. And if we simply take, for example, this variable platelets, the mean is in the order of 100,000, whereas the serum creatinine has very small values. Therefore, normalization is going to be required. So that's something to just keep in mind for the next step. In order to have a more visual representation of these values, we are going to understand the data through visualization. Given the fact that I have multiple variables in the data frame, the first thing that I'm going to run is not going to be univariate analysis, because in my opinion, doing this first is just going to be a waste of time. Instead, what I'm going to do is select all the numerical variables and do a pairs plot. So the reason why I am starting with straight with a pairs plot is because pairs plot offers me this univariate analysis that I need at the variable level. So I can see here the histograms of each one of my numerical variables. I can identify those distributions that are skewed. I can identify the bimodal distributions. And at the same time, I also have access to the scatter plots, where every two variables are plotted against each other. So, for example, this first plot is just plotting the age against the creatinine phosphokinase. The next one is plotting the age against the ejection fraction, and so on. Moreover, if I include the target variable to my data set, now I can add the hue as this categorical variable. So this is what I mean. On the right hand side, I have the legend. At the variable level, I have the two distributions of the people who lived and those who died of cardiovascular diseases. And then also in the correlation, I can see straight away whether there is any variables who can distinguish very good between the two groups. I can also have an impression of how many outliers there are at variable level. For example, here in creatinine phosphokinase, I can see that the distributions are strongly skewed to the right. These outliers are reflected also in these high values in the scatter plot. So I can do this for every variable without the need of plotting manually each one of the variables and then each pair of variables. If I nevertheless would like to plot, for example, the age distribution by death event, I could do this with Seaborn, with the histplot method, where data is my data, x is what I'll be plotting on the x-axis, and here, because I'm talking about the distribution of age, it will be age. I can add more to it. For example, I can color, or I can divide the distributions by a binary variable, for example, by death event. I can add density estimation. If I choose nevertheless to generate these plots one by one, I can do it. If I want to generate a scatter plot, I can do it with scatter, specifying the data frame name, and then I can specify the variables that I want to plot against each other. Let's say the serum sodium is going to be y, and on the x-axis we are going to plot another numerical variable. Let's say serum creatinine, scatter plot, sorry. Okay, so now we have the scatter plot between the two variables. I can add the hue parameter with a categorical variable if I want to visualize the cloud point by categories. Additionally, what I could do is draw a line. So instead of a scatter plot, I can try to build a linear model plot, which is going to approximate a linear regression for each one of my groups. From this scatter plot, I can see that I will need to apply some preprocessing on the serum creatinine variable. Probably I'll have to logarithmate it just to spread a little bit these points in the upper left corner. Okay, so now that we've plotted two numerical variables against each other, we can also plot two categorical variables against each other. I'm going to use a violin plot, the E violin plot, to do it. My data frame is the same. On the x-axis, I'm just going to represent the gender, and on the y-axis, I'm going to put the smoking. And I see here that the female group actually seem to not smoke. So the majority of the females are non-smokers, and there is a minority who are smokers, whereas for the male, the groups are quite equal. Add a third variable, which is the death event. Now the blue ones represent those who lived, and the red ones those who died. But now the question arises, what if we want to visualize all these risk factors as a flow, or as a tree that starts with the gender and then goes through all the risk factors and then ending with the death event? Is there such a diagram? The answer is yes, there is such a diagram. It involves quite some manual work, so I'm just going to use the code that I have already written, a hard survival Sankey diagram. So this is what I mean. This diagram is very useful because it also gives an impression on the class distribution. For example, here we start with the female. We can see clearly that the smoking group is very small, the same that we saw in the violin plot. And then we can just go by each one of the branches and see whether these cumulating risk factors lead to a death event or not. If we want to calculate the correlation between each pair of variables, we can achieve this very easily by using the core method. The first thing we must do is slice our data frame such that it contains all rows and all columns except the last one, because the last two columns are exactly the same. And we are just employing the method core. And this will give us a table where each cell is the correlation between two variables. Instead of looking at those numbers, I can have a better intuition of the strength of the correlation by just using a heat map. So here on the diagonal, I see that I only have correlations of 1. That's perfect correlation. And that happens because on the diagonal, I have calculated the correlation between each variable and itself. So age against age is going to be perfectly correlated. Also bear in mind that 0 is not the darkest color, so it's here around the middle of the scale, and then the darker the color gets just indicates that the correlation is negative, and the lighter the color gets, it indicates that the correlation is positive. Okay, so this would help a lot, for example, for first of all checking which are the variables that are really influential on the death event, which might be our target variable. But it also helps, for example, in the variable selection step or in the feature engineering step, as if the variables are highly correlated and they are both included in the model, then it might be that one takes over the entire variation in the model, whereas the other one is left with not much. One last thing that I want to share with you refers to visualizing the outliers. Box plots are very good at visualizing outliers. For this example, we are just going to take two variables, one numerical variable and one categorical variable. And we see here that there are a number of outliers. These can also be visualized in the pairs plot, in the scatter plots, or in the histograms of the numerical variable. You can just exchange it by hue, and then we have also like different colors for it. From this plot, besides visualizing the outliers and being able to even identify the outliers or extract them, we can see that the serum creatinine is going to have an effect on whether a person is going to survive or not a heart disease. Another example that I want to show you is this. So ejection fraction is also going to play a big part in whether that event is going to occur or not, because the boxes are not overlapping at this level. So now let's summarize all our findings. From the structural point of view, the dataset was reduced by removing the duplicates and the non-values. Out of the 8 rows containing none values, 7 rows had only missing values across all columns. In the reasoning step, the analysis of the variable data types are adjusted such that they make sense. 7 out of 13 columns are Boolean and 6 are numerical. 2 columns encode the exact same information differently, one as Boolean and one as text, and some string processing is needed for ensuring data consistency. The next steps to take in terms of data processing are normalization, because of the different ranges of the variables, applying data transformation on some of the numerical variables, and taking a decision with respect to the outliers, whether it involves further investigation or removal. Potential questions to choose from are the risk factors predicting whether a person will live or die? Do males have riskier behavior than females with respect to their health? Or does age play a role in engaging in riskier health behaviors like smoking or obesity? Any of the questions are classification problems, so any of the following algorithms could work: logistic regression, random forest, XGBoost, or neural networks.
When I first started off with data science, I would spend days exploring the dataset, losing track of my ideas as new questions were coming to fore. Curiosity was taking me places and leaving me there feeling lost, not being able to summarize my ideas. When we look at the traits of the great explorers of the world, curiosity is among them, but it would be nothing without structure, focus, and collaboration. Things fell into place for me once I added some structure to the process and embraced the idea of discovering as I go, answering only one question at a time. I hope some of these ideas will help you structure your exploratory data analysis process as well, such that you never feel lost or overwhelmed with data again. Hope to see you next time. Remember, practice makes better.